Okay, so welcome everyone. It's a great pleasure to have Dror coming from Toronto and for an exceptional seminar. And he will talk about, well, shifted partial quadratics. You have the whole title in front of you. Actually, you have the whole talk in your hands, I hope. If you don't, ask him for the handout when you are. So, Dror, the floor is yours.
Yeah, something was not right, so I'm trying to fix it. Where is my timer? Okay, something is not showing, you know. Let me put it full screen again. What? Where is it? Okay, sorry, something is messed up with my laptop. Just 1 second. I think I just reload. Make it full screen. My screen doesn't match that screen. So okay, it doesn't matter. Let's make do with what we have. Okay. So, sorry about that. So, first of all, my talk follows a handout. Oh. And I hope you all have a copy. Sorry, and now it is showing. Okay, sorry. I hope you all have a copy. Second, maybe I'll start from the embarrassing point right away. So, 2 days ago, I found that there is a bug in the way I was thinking about Theorem 4, and I'm almost sure I know how to fix it. And also, I'm absolutely confident that the theorem is true because it's verified with computations. It matches, and it fits perfectly with everything, but there is still a small gap, so I have to be honest and acknowledge it. Next, so you actually didn't invite me, I invited myself. So thank you for allowing me in Geneva. And also, if you look at drorgen.net/GE23, you'll find this handout and everything else I will talk about, maybe the video as well. Everything I will talk about is joint work with Jessica Liu. And the picture on the handout is much nicer than the picture here. Something is wrong with the projector. There is prior art. So I'm going to talk about, maybe I should have said that at the start, signature invariants for tangles. And there is prior art, including by people sitting in this room, David, namely. And David, please forgive me. I think this is cleaner. Maybe it isn't. Maybe you will decide. Well, you will be the judge. But I think at the end, this is a cleaner way of saying the results. And I have to acknowledge the NSERC and the two family foundations in New York City that are supporting this work. And now I can start. So again, the main piece is I will tell you about recent work with Jessica about what we think is the textbook extension of knot signatures to tangles. But this will follow a general discussion of the computations of zombians of unfinished columbaria. And since many people don't know these words, let me explain. So a columbarium is a burial structure where it has lots of cavities. It's a structure, it has lots of cavities, and in each cavity it has a place to put an urn with the ashes of a dead person. An unfinished columbarium is a columbarium, some of whose cavities are not yet filled in. Okay, so we still don't know what names go into some of the cavities here. Okay, and a zombian is something that zombies want to compute. So, you know, there is Lagrangian, Vronskian, Hessian, zombian. That's what zombies compute. The point is, so you have a columbarium, and of course, the computation is on columbaria, the plural of columbarium, And how the output is somewhere else, I don't know. But the point is, suppose you have an unfinished columbarium, what can the zombies compute today so that when the new information comes in, I don't want to tell you what it is, then they will be able to complete the computation faster. Okay, so 2/3 of the information is given. What can you compute today so that when more information comes in, you will be able to complete the computation of the zombian? So the motivation comes from knot theory, where for many things in knot theory,
To the left.
For many times in knot theory, you want to compute some quantity, I don't know what, associated with some complicated knot. And, but sometimes the knot is half given, so only the part below the line is given. And then you want to know that, and that by the way is called a tangle. So kind of half of a knot in half the space is called a tangle. And then the question is, what if a tangle is given, what can you compute so that you'll be able to complete the computation later? So before doing anything, why tangles? So it actually is often much faster, especially when you're talking about exponential time algorithms, but also if it's polynomial time sometimes. So basically, if you know the Kaufman bracket, for each crossing of the knot, you get to choose between two smoothings. So you have two choices to make. So the overall number of choices is 2 to the n, where n is the number of crossings. Now, if you're able to cut the knot in half, so you get a tangle on the left, a tangle on the right. On the left, you have n over 2 crossings. On the right, you have n over 2 crossings. And then the time to compute will be 2 to the n over 2 plus 2 to the n over 2, which is a lot less than 2 to the n, so you've saved dramatically. I'm actually lying, because there will also be a cost associated with gluing the two pieces. But typically, if you have a knot with n crossing, I mean, you can think of it basically as if it's an array of size n by n of mass, and then if you cut it in the middle, it will be, square root of n by square root of n, and if you cut it in the middle, then you expect to see the cut of size square root of n. So even if the cost is exponential, or the cost of gluing is exponential in the size of the cut, you will pay 2 to the square root of n, and 2 to the n over 2 plus 2 to the n over 2 plus 2 to the square root of n is still a lot less than 2 to the n. So you've saved a great deal. Also, you get conceptually clearer proofs of invariance. So, you know, in knot theory, invariance is proven by showing that the 3 Reidemeister moves. And the 3 Reidemeister moves, sorry, can I assume that people know what they are? Okay, are basically moves between tangles. So if you understand tangles, if you know an extension of your invariant to tangles, and you show that for the tangle on the left-hand side of the Reidemeister's move, it's equal to the tangle on the right-hand side of the Reidemeister move, then you've proven invariance and it can be conceptually clearer. And maybe the most important thing is that it's often fun and consequential. Extending to tangles, yes?
Sorry, it's oriented or unoriented?
Oh, at the moment I'm so I'm so vague that it doesn't matter. I think oriented. My notes are oriented, yes. But and it's often fun and consequential. So basically, if you have the Jones polynomial, it's a polynomial. If you care about the Jones polynomial for tangles, you're led to studying the temporally Lieb algebra. If it's Chovanov homology, and you cut the knot in half, then the things you see in each half are no longer chain complexes, are no longer vector spaces and maps between them. There are half-defined vector space and half-defined maps between them. So this leads you to thinking about complexes in a category and various other, basically it's always exciting. The Kontievich integral leads you to think about associators. Higard floor homology, if you cut it in half, leads you to think about, oh my god, I don't want to even say. And let me say that in practice, the right way to go is often not to cut in half and then cut the half in half and then cut the other half in half and so on. Often the right way to go is what I like to call knot tease. So knot tease is you put the knot behind the curtain and then you slowly raise the curtain. And as you slowly raise the curtain, you see more and more of the knot. So like one crossing joins and then a little later a second crossing join and so on. So at each stage you see a tangle. And the challenge is to figure out, given a small tangle, how to compute the invariant of a slightly bigger tangle. So if you add ashes to the columbarium, one cavity at a time, one urn at a time, how do you proceed with the computation? Okay, so sorry, I'm still in general philosophy, but it will become concrete mathematics at some point. So, what are the conditions for computing the Zombian of unfinished columbarium? So first of all, you must be at least no slower than computing the complete thing, because otherwise the way to compute would be to wait until all the information is given. You will not save anything by computing something early. Clearly, I want future zombies to be able to complete the computation. Here's a nice thing. I want future zombies to not even know how much the present zombies have computed. So basically, I have my zombies. Sorry about the quality of the picture. The picture on the handout is nicer, but the projector kills it. So I have a columbarium here, and I have the zombies running, going up and computing more and more and more. And basically, I want the information that the zombies at a certain height need to consider. I want it to be proportional to what is visible at that height, and I don't care how much stuff there is below. Okay? So this is basically the parallel of saying that as I compute along the knot, I want to be thinking about information of size square root of n, not of size n. Okay? And finally, we must be able to extend, so not only compute stuff for columbaria, we need to know how to compute stuff for ZPACs. So zombie processed unfinished columbaria. So, you know, the zombies process the columbaria, give you an output. Now, this output is the input for the next stage, not the tangle itself. So I need to be able to whatever I compute, I need to be able to extend it, not only to compute tangle invariants, but also to compute what's already been out, based on what's already been output. Yes, Anton.
So I have a remark about fancy words.
Yeah.
So certainly those spooks, that's a good thing.
Yeah.
But physicists some time ago, they invented the word of holography. Isn't it like something like that? You're saying that you have a region bounded by something, right? You have a boundary, and the complete information, it looks like, right? Supposed to be contained, right, on that surface where your zombies are standing.
Yeah. So maybe what you're giving is an even fancier example than the examples I already gave. But I want to do it for something concrete. I want to do it for signatures. But before doing it for concrete, for signature, let me challenge you. So I give you a 1,000 by 1,000 matrix, but I'm telling you that 50 entries are not yet known. Okay, so what do? So
And there the And now you say compute the determinant, right?
Sorry?
So, but what do you do? But
I want to compute the determinant.
Yeah.
Sorry, I should have said. I want to compute the determinant. I have a 1,000 by 1,000 matrix. This is the scale of the things that I look at. So I have a 1,000 by 1,000 matrix, and 50 by 50. Sorry, 50 entries are not known. What can I compute now so that I will know the answer, so that I will be able to continue later and save something? Any suggestions?
the complement, whatever, complement determinants of those 50 elements?
But it's not, the complement is not a matrix. It's
No, but I mean, you cross one, as usual, one line and one
so
one
the
bar.
minors, basically.
Yeah.
The problem is that if you have 50 entries,
Yeah.
you need, well, you also need the bi-minors when you delete 2 of them, and the number of minors that you end up needing to consider is 2 to the 50. That's a lot. That's much more than the computation time for the determinant of a 1,000 by 1,000 matrix. Here's another suggestion that I often get. So basically, you compute, you put variables in the missing places, and then you compute the determinant in the polynomial ring. And then when the values are known, you just substitute these values into the polynomials. But this is essentially the same, I'm just saying it differently. The problem is that you'll get a polynomial in degree 50 in a polynomial ring with 50 variables, and the number of such things is again exponential in 50. So forget it. So here's what you do instead, or here's one thing you could do instead. First of all, you can, by row and column operate, yeah?
Can you just put everything you don't know on one side and
That's
start
exactly what I'm
Gaussian?
going to do. So first of all, you put everything you don't know into, by row and column operation, into the 50 by 50 blocks at the bottom, block at the bottom. And in fact, I'm going to tell you what to do, assuming that this whole block is unknown. So 2,500 things are unknown. So this block is unknown, and these blocks are A, B, C, and I'll tell you what to do. In fact, it's on your handout, except it's printed in small characters, so you didn't see. So, how do I compute the determinant of a matrix A, B, C, U? U stands for unknown. I do row operations to A until it looks like the identity. That just means multiplying on the left by something. Row operations is to multiply on the left. So I'm multiplying on the left by A inverse. So I need to invert A. Inverting a matrix is cheap, is Gaussian elimination exercise. But I get I A inverse B. Then I take these rows, multiply them by C, and add and subtract from the rows here. So I get the identity A inverse and then U minus C A inverse B. Now, when you compute determinants using row operations, you know, when you multiply a row by 7, you have to divide the end result by 7. So when I multiply by A inverse, I'll have to multiply the end result by the determinant of A. And then here I do adding rows to other rows. This doesn't change the determinant, so I have to multiply by 1. And then the conclusion, and then what I get here is a block triangular matrix. So the determinant is the determinant of the identity plus the determinant of that. So the formula I get is that the determinant of the original matrix is equal to the determinant of A times the determinant of U minus CA inverse B. And now, what do the present zombies pass to the future one? They pass the determinant of A and the value of CA inverse B. CA inverse B is in the lower right corner, so it's a 50 by 50 matrix. So they're passing a small amount of information, proportional to what remains, not to what has been done. And given this information, the future zombies, once they know you, they take you, they subtract to it what they got from the previous ones, they compute the determinant, that's a relatively easy thing, the determinant of a 50 by 50 matrix. They multiply by the extra scalar that was given, and that's the output. That's lovely, I love it. I love it, it's nothing, it's high school algebra, but it's lovely. Anyway, roughly, so later, I will be thinking of like as if I have a big vector space V and a small part of it W, and there is some projection from V to W, namely you drop the first 950 coordinates. And roughly speaking, the determinant of A is the determinant on the kernel of the projection, and minus CA inverse B is sort of a push forward of the original matrix from a matrix on V to a matrix on W. This is loose, and it will become precise for signatures in a moment. Okay? So now,
Sorry.
yeah?
There was a question in your hand, which was, what if A is not invertible? But
Yeah, so I'll make it harder. First of all, what if A is not invertible?
Gaussian
And
image.
secondly, I'm asking you, no, but what is the, okay. Secondly, what if you get partially processed things? And finally, can you use this to get an Alexander invariant for tangles? The Alexander polynomial is a determinant of a matrix. If you have a tangle, half the matrix is given. Can you get an Alexander tangle invariant using this? But this is homework. But now I want to end of philosophy, and now I want to start talking about the actual signatures. So first of all, let me remind you what are signatures. So given a note, so here are two signature formulas. So given a note, here are two ways to get a signature invariant. So in both ways, you write the note in the plane, you label the faces of the note, so 1, 2, 3, 4, 5, 6, up to 10, and then you make a 10 by 10 matrix, so basically a matrix whose rows and columns correspond to the faces of the note, and it's a Hermitian matrix or a symmetric matrix. Sometimes there is complex conjugation, sometimes there isn't, but it's basically a Hermitian matrix. And then what you do is you simplify the way you simplify Hermitian matrices, so you do row and column operations, but you do them in tandem. So when you do a column operation, you do the corresponding row operation as well. And this is what these interlocking wheels mean. Whatever you do here, you also do here. Doing this, you can simplify the matrix to a matrix of the form 1, 1, 1, 1, and suppose you have sigma plus of those. And minus 1, minus 1, minus 1, and suppose you have sigma minus of those. And then a bunch of zeros which you ignore. And then the signature is defined to be sigma plus minus sigma minus, sometimes plus a little shift that I will explain later. Okay? And, but the shift is very, very easy. It's trivial relative to that. Okay? Now, I'm going to tell you about two such maps from notes to matrices. One is computes the Tristram-Levin signature, though the map is not due to Tristram-Levin. And the second one is the Kashayev map, like this. Okay? So all I have to tell you is, so the way it works is each crossing is surrounded by 4 faces. So for each crossing, I will give you a 4 by 4 matrix that only involves the 4 faces around it. And then the matrix for the whole knot will be the sum of the 10 matrices, no, 8 matrices in this case that you get for the 8 crossings. Okay? And so all I have to give you is those matrices, and here they are. So first of all, you start with a complex number of modulus 1, and then just to make the formula simpler, I will write t to be 1 minus omega. I will write r to be the twice the real part of t, so t plus t conjugate. I will say v is the real part of omega, and u is the real part of the square root of omega, and it doesn't matter which one you choose. And then, if you have a crossing, and it is surrounded by faces I, J, K, and L, ignore the minuses. These are for a technical reason in the implementation, not for the mathematics. So if you have faces I, J, K, L, then you add to the matrix A in rows I, J, K, L and columns I, J, K, L, this matrix. And if you have a negative crossing, you add that matrix. This is to get the Tristram-Levin signature. To get the Kashayev signature, it's exactly the same story, except the matrix is you add this particular matrix on the for a positive crossing, and for a negative crossing you subtract this matrix. But you also have a shift in this case, and the shift is -1 for positive crossings and +1 for negative crossings. So that you add that shift at the end. But again, that's a triviality relative to the signature. Okay? That's it. I've defined the two signatures. So I should say that Kashayev's conjecture, which is now Liu's theorem, says that for knots, the Kashayev signature is twice the Tristram-Levin signature. I'm not going to tell you anything about how to prove this conjecture. This is the work of, this is Jessica Liu with some further work by David Simasoni and Liviu, and that's a completely different story. Okay? Okay, so next I'm going to state a theorem about pushing forward quadratics. But I think I want to give you the proof of the theorem, or the gist of the proof, the main point of the proof, before stating the theorem. So the basic idea is roughly like this. So you have a matrix A, B, C, except our matrices are Hermitian, so C is just B transpose conjugate, and an unknown piece U, and you want to compute, sorry, this matrix represents a quadratic form. It's called Q. You can see Q in the background here. And you want to compute the signature of this quadratic form. This quadratic form is defined on a vector space V, whose basis corresponds to all of the rows or all of the column of this matrix. Think it's 1,000 by 1,000. And the part which is still unknown, I'll call it U, and it corresponds to a part of the space which I will call W, and I will think that there is a projection map from V to W. So what do I do? Well, I do exactly what I did for determinants. Namely, I try to simplify with row and column operations. So first of all, I do row and column operations in tandem. So row operations at the same time, the same column operations, to A, to bring it to the form plus or minus ones of the diagonal, 0, and then zeros the rest. Then I can do column operations to use these ones and minus ones and kill a part of B. But a part of B stays. I cannot kill it. Like the part of B that is next to the zeros I cannot kill, so it stays. Now, well, I do the same thing, whatever I do to the columns, I also do to the rows, so there is a C here and a C conjugate transpose here. Then, but as I do it, you know, so when I add columns from here to here, stuff gets added to U. So as I do it, some F gets added to U, and in fact, F itself remains Hermitian. So at the end, I get two pieces of information. One piece of information is the signature of the A part, and this is roughly the signature of Q restricted to the kernel of the projection map to W. And I get a piece which I think of as the push forward of the original quadratic form to W. Now, what is this? What I get is a Hermitian matrix, kind of W by W, but I also get a piece C. By doing row and column operations to C, I can make sure that the rows and columns of C are linearly independent. So, you know, if this was 50 by 50, C is going to be less than 50 by some, is going to be 50 by less than 50. So it obeys my information restriction. It's not going to be of size 1000 by 50 by 1000. Okay? So C is relatively small. But this whole thing is not fully determined because I still have the freedom of adding a rows from C to F and correspondingly columns from C conjugate transpose to F. So this is this bevel gear. It's whatever you do. Oh, sorry. So you can mix C inside as you please. You can mix correspondingly the C conjugate transpose. And you can add things here and add in tandem with adding things from here to here. So what is it that you're left with? So this defines a quadratic, but it's only well defined on the kernel of C. Because adding rows from C to F is not changing the values on the kernel of C. So you get a quadratic which is defined on a kernel, so it's partially defined quadratic. And now that we've seen the proof, let me state the theorem. So, definition, a partial quadratic on a vector space is a quadratic defined on a subspace, the domain of, just on a subspace. And then, if you have two partial quadratic, you add them by intersecting the domain. And if you have a linear map from V to W and a partial quadratic on W, then obviously you can pull back. Pulling back is obvious. In fact, kind of the whole fun of this topic is that pulling back is always obvious, but what is surprising is that you can also push forward. This is not something you expect. And anyway, the theorem is that given a linear map phi from V to W and a partial quadratic on the domain, there is a unique push forward quadratic, and the property of the push forward quadratic is that whenever you have a partial quadratic U just on W, you have that the signature on the whole thing of Q plus the pullback of U, Q plus the pullback of U is precisely basically it's this with a C plus U here, where C is some like Q also is allowed to have a piece here. Okay, and then this signature, so this is the thing we wanted to compute to start with, is equal to the signature of Q restricted to the kernel plus the signature on W of U plus the push forward. Again, if you look at the proof, that's exactly what we get. And if you really must, here is a few lines that write what Q is, but I don't want to do it. Okay. Now, for knot theory, this is exactly what we want if the overall zombian is the signature. Why? So basically, suppose you have a tangle. Here is a tangle. Right, you can see I made it a simple weave, okay? But a tangle divides the plane to faces. Now, some of these faces are internal, but some of the faces are on the edge. The faces that are on the edge, I will call gaps, because they are the gaps between two edges between two strands that come to the end, to the side, okay? So, the vector space V is the full space of faces, because if I run the Tristram-Levin procedure or the Kashayev procedure, I get a quadratic, but I run it only on the tangle, I get a quadratic form on all the faces that appear here. W is the boundary, so it's the gaps, Q is the part of the quadratic I already know, and U is the parts that are unknown, and the parts that are still not known are going to come when I connect this further, and then the only thing that get affected might be the values between the value of the quadratic on or the bilinear form on two W's that are on the edge, on the boundary. So only on so U is a quadratic form on just the gaps, on just the vector space W, and then the signature of Q plus the pullback of U, you first have to pull back U to be a form on the whole space. I mean, this is the overall signature, and the signature of the kernel, or of the quadratic form restricted to the kernel, is the signature kind of only the face of whatever happens only on the faces inside, and that's an internal bit, and you pass it to the future, you pass it to the next zombians. This is a boundary bit, so U plus the push forward of Q is defined only on the boundary, and again you have to pass it to the future. And so the zombie process unfinished columbaria is the pair, the signature on the inside, plus, comma, the push forward of Q to the boundary. Okay? Now, but this tells you that the thing we really want to deal with are not quadratic forms or partial quadratic forms, but quadratic forms with an additional integer, which I will call the shift. And then I come to the next definition. So a shifted partial quadratic is a pair, an integer, comma, a partial quadratic on the vector space.
Sorry.
Yeah?
Do you have some information on the dimension of weight? The dimension of weight? Arbitrary?
I mean, arbitrary, yeah. I mean, so what I wrote works for every dimension, but for a specific tangle, the dimension of V will be the total number of faces, and the dimension of W will be those faces that are near the boundary, so the edges. But the theorems are general. Okay? So, so a shifted partial quadratic is a pair, integer, comma, partial quadratic. When you add the shifted partial quadratics, you also add the shift. When you pull back, you keep the shift. When you push forward, so the way you push forward is you push forward the quadratic part, and you take the shift and you add to it the signature on the kernel. And finally, the signature of a shifted partial quadratic is defined to be the shift plus the signature of the quadratic piece. And then a reformulation, the exact same theorem that I wrote before, reformulated in terms of shifted partial quadratics. So this is theorem 1 prime, because it's exactly the same. I mean, it's just renaming of things. So it should be called quadratic reciprocity, because it's a theorem about reciprocity between quadratics. But I can't do it, so I'll just call it reciprocity. Okay? So given a map from one vector space to another, and shifted partial quadratics S on V and U on W, then the signature on V of S plus the pullback of U is equal to the signature on W of U plus the push forward of S. Now the shifts are included, so I don't need the extra term. And in fact, this fully characterizes the push forward. Okay? Note, pullback is an additive operation, but push forward is a highly nonlinear operation. Okay, so it's not, okay? However, here is the proof of theorem 1, written in the language of abstract mathematics, but I no point to go over it, no time also. Okay? But there are more theorems. So pullback is functorial. So if you have a pair of maps and you pull using the first and you pull using the second, it's clearly the pullback using the composition, maybe in the reverse order. But this is tautology. No. But the claim is that push forwards are also functorial. So if you push and then push again, it's like pushing by the composition. That's not obvious. And in fact, here is the proof. It's not obvious, but it follows immediately from reciprocity. So basically, since push forwards are defined using reciprocity with pullbacks, and since pullbacks are functorial, push forwards are also functorial. Then there is, oh, sorry, I was going to tell you about, sorry, I forgot to mention that there is also theorem 3. So theorem 3 says that under some restriction, so if two of the maps in a square are surjective, then push forward and pull back roughly commute. So basically, if alpha and gamma are surjective, and if you have a quadratic form here, then pulling and then pushing is the same as pushing and then pulling. And again, the proof is here, and it's a bit harder. But yeah.
Yeah, I have an association which I'm not sure how valid it is, but so since you have those quadratic forms or partial quadratic forms, can we also reformulate it in terms of, you know, subspaces in the sum of your space and its dual, right? Because that defines for you some maps between, I don't know in which directions, between the space and the dual, and this means that it gives you some kind of, you know, it's a little bit sounds analogous. There are all those whatever Dirac structures, or this push like whatever your colleague Marco Gualtieri, this generalized geometry, whatever. It sounds a little bit.
I don't know.
Okay.
I don't know. No, it doesn't ring a bell. Mm-hmm. Though it may well, it's possible that this does ring a bell, mm-hmm. and maybe I'll comment on it later. But okay. Anyway, right. Now I can go back to Tangles. So now I want to define a signature invariant for Tangles. So given a tangle, I have to tell you where it takes values. So if you have a tangle, I write the boundary in green, and then the tangle has gaps, G1, G2, G3, and so on. The space in which the tangle invariant takes values is shifted partial quadratics on the space generated by the GIs. But now I need to tell you how to, so suppose you have two tangles and you compose them, I want to tell you, if you know the invariant here and you know the invariant there, how do you get the invariant of the composition? But composing tangles is much harder, or not much harder, much richer than composing in a group. In a group, you can only multiply from left to right. If you have tangles, you can stack them left to right, you can stack them up above each other, you can stack them diagonally. In fact, the way to describe how to multiply two tangles is to give, or three tangles, is to give a so-called connection diagram. So here is a connection diagram. A connection diagram is a disk with a number of holes labeled 1, 2, and 3, or in general more. Okay? And the holes are where you, so if you have 3 input tangles, you plug the first into here, the second into here, the third into here. The connection diagram also has connections between the ends of 1 and the ends of 2, and between the ends of all of these and the output. And then if I put a tangle in here, another one in here, another one in here, I get a big tangle, which is a composition of all of these, of the input tangles. And these operations together make a planar algebra. This is called a planar algebra. So a planar algebra is basically a structure where you can multiply again to the left and to the right, but also up and down, and then the set of all multiplications is parameterized by connection diagrams. Now, if you have a connection diagram...
Sorry, what is F?
Oh, I didn't say it. If you have a connection diagram, I can label various parts of it. So basically it has faces, and I will label the faces F1, so F1, F2, F3, F4, F5, F6, F7. And it also has the gaps of the input tangles, so I will call them the input gaps. So the gaps of tangle number 1 will be G11, G12, G13, G14. The gaps of tangle number 2, G21 up to G26, whatever it is, or 4 also. Likewise for 3. And finally, there are the output gaps, the gaps of the output tangle, and I will call them simply G's. So G1, G2, G3, G4, and so on. Now, there are 2 maps. Oh, I think this is already here. There are 2 maps that go from the faces to the gaps. There is the going in map and the going out map. The going in map I will call psi, and psi map each face to the sum of the in gaps that are next to it. So F2 is next to G14, G24, G33, and G31. So F2 gets mapped to G31, G14, G24, and G33, plus sum of all of those. And the second map is the map phi. And the map phi is the map which maps every face to the sum of the output gaps that are next to it. So F2 will be mapped to G2 plus G6. So phi maps F2 to G2 plus G6. And then I will define a composition operation as follows. So the composition operation is, so if I have 3 input, not tangles, because by now I've computed their invariant. So I have 3 input shifted partial quadratics. I look at their direct sum. It's a shifted partial quadratic on the space of in gaps. I pull it back using psi to the space of faces, and I push it forward using phi to the space of outgaps, and this is the output of the operation. And the theorem is that this makes a structure of a planar algebra. What do you need to prove? So you need to prove the operad property. So basically, like this is a composition of 3 tangles, but I could do it in 2 steps. I could write it as a composition of 1 and 2, then composed with 3. So you need to show that whenever you have a composition of 2 planar algebra operations that can be written as a single planar algebra operation, then the composition is the composition, is the result. What goes into it? So if you have a composition of 2 planar algebra operations, so the first one is a pullback followed by a push forward. The second one is a pullback followed by a push forward. So you get pull, push, pull, push. I want to simplify it and write it as a single thing. So pull, push, pull, push. You swap the order of the middle 2 and it becomes pull, pull, push, push. Then you use functoriality and it becomes pull, push. And pull, push is a single operation. So that's what goes into the theorem. And the reason I put a question mark is that I forgot to verify one of the conditions. So, because the theorem 3, I believe, had a condition, and there is an issue there. But again, the evidence is overwhelming that it's true, and I think I know how to solve it, except I only think I know how to solve it since this morning, or since yesterday, in fact, since yesterday midday, because I only found the problem the day before, so I don't feel confident enough to remove the question mark yet. Okay? And finally, there is a theorem that Tristram-Levin and Kashayev defined on the positive crossing and the negative crossing as before, extend to morphism of planar algebra from the planar algebra of tangles to the planar algebra of shifted partial quadratics. Okay. Since I always make mistakes, I tend to always implement and run things. And in fact, to me, a running program is even a better verification than a proof. In a proof, you can make a mistake. If you run a program and it runs for everything, then it's right in practice. So, but unfortunately, so I do have an implementation, but the best is if the implementation is like visibly the same as the theory. But it isn't for this implementation. So in a sense, we failed. So basically, the theory, I wrote the theory in terms of planar algebras operation. But the implementation is in terms of knot T's or tangle T's, where you add the crossings one at a time. So well, that's my failure, sorry. Here is the implementation, lots of code. In particular, the atomic operations are not the planar algebra operations, but sort of attaching 2 tangles next to each other and also cordoning off a part of a tangle, so basically connecting 2 adjacent legs of a tangle. And it turns out that these are the atomic operations. With these operations, you can write everything. So this is the hardest part of the implementation, and here it is. It is hard, it is not so easy, unfortunately. This is the rest of the implementation, and in particular, you can see here the Kashayev matrices and the Tristram-Levin matrices. And, here they are. And here are some runs. So you run the programs on the 2 sides of the Tristram-Levin, of the Rademeister 3. You run the Tristram-Levin for the left-hand side and the Tristram-Levin for the right-hand side. And you ask the computer if they're equal. The computer says true. And so the Tristram-Levin signature is invariant under Reidemeister 3s. Likewise for the Kashayev signature. Likewise for and by the way, if you care to see the intermediate, so this is the value of the Kashayev signature of one side of the Reidemeister 3 move. Well, the left-hand side, but it's the same for the right-hand side. So the value is a quadratic form or a 6 by 6 quadratic form, because there are 6 gaps on a Reidemeister 3. The subspace here is trivial, the subspace is the full space, right? It's a partial quadratic, it's defined on a subspace. But the subspace is the full space, so it's not indicated. But there is also a scalar part, basically the inside signature, and the inside signature is written here, and it's a function of u. U was the real part of omega, and it's in fact a sum of theta step functions. So it's twice the step function of u minus a half minus, well, whatever. Okay? So this is what the output looks like. Then you can do the same for Reidemeister 2. Again, the computer outputs true, which means that the invariant is invariant. The two invariants are both invariants under Reidemeister 2. Then you can do the same for Reidemeister 1. And again, we've now proven invariance. Now you can, if you want, you can compute the value for a knot. For a knot, the quadratic form is on an empty space, so it's just 0 by 0. You don't see anything, you only see the scalar. And the scalar is a sum of theta function, and if you plot it, you get one of those familiar graphs. Here's the Conway-Kinoshita-Terasaka knots. These are the two knots that if you glue them in two different ways, you get the Conway knot and the Kinoshita-Terasaka knots. So, you know what, I'll skip it, but you know, you can just compute whatever you want. And maybe I'll tell you about things with non-trivial dimension, codimension. So where the partial quadratic is really partial. So here are two braids. I found them by just searching on all braids. And braid number 1 written as a tangle is written here. Braid number 2 written as a tangle is written here. And if I look at the Tristram-Levin signature of braid number 1, I get this. So this is a quadratic form on a 1, 2, 3, 4, 5, 6, 7, 8 dimensional space. The inside part is 0. And I have 2 rows at the top above the labels of the gaps. And the 2 rows at the top indicate which subspace it is. So in fact, the subspace is the kernel of the matrix with these 2 rows. So it's a subspace of codimension 2. So sometimes you get a subspace of high codimension. For the Kashayev invariant, the subspace is only codimension 1 for the same braid. And for the other braid, B2, the braid number 1, the Tristram-Levin, the codimension is 0, but the Kashayev, the codimension is 1. And here are the coefficients that define that subspace. So I'm just saying you can play. And then I have lots and lots of questions. Is there a topological meaning? Is there a Kashayev conjecture for tangles? Well, for knots, it's no longer a conjecture. For tangles, it's not yet a conjecture. Okay? And I have many, many other questions. Maybe I'll say one more thing. Is it okay? I'm not sure if I'm out of time or not because, okay. So, I'll say one more thing. So you know, when David asked me for my title, I tried to delay it because I wanted to talk about something else. I wanted to talk about the same story for the Alexander polynomial. And it's half done, it's not done, so I can't talk about it. But basically, it's roughly the same story, but for determinants instead of signatures, and it turns out that there are complications. But really, what does it but do you know it? Do you already know it? I mean, is there any sense in which there is a genuine push-forward operation, not like what I wrote here, which was a schematic, but a genuine push-forward of quadratics, such that you can compute, compute the overall determinant by first pushing forward, keeping some determinant on the side, and then computing the determinant of the end result. And the answer is, yes, it's called computing the marginal of a Gaussian distribution, or basically computing Gaussian integrals, or basically, taking the expectation value, the conditional expectation of a Gaussian. So if you have a Gaussian defined on a space, the integral of that Gaussian is roughly the determinant of the quadratic, maybe 1 over the square root of the determinant, but it's the moving part is the determinant. So again, but on the other hand, you can use Fubini and compute the determinant in 2 steps, and when you compute the integral in 2 steps, and when you integrate on the fibers, if you take a Gaussian and integrate it on the fibers, the result is again a Gaussian, and that is in fact the push forward of a quadratic. Except this gets you in trouble with zero modes if you integrate in a direction in which your quadratic is degenerate. And unfortunately, you cannot avoid it. So you are led to trying to invent a theory of Gaussian integrations that will be complete, that will work even if even if your Gaussians are degenerate on the fibers. And sometimes, and you get sometimes you integrate on the fiber and the fiber is degenerate, but the overall thing isn't. So you can't just throw away degenerate stuff. Also, when the integral of the quadratic e to the I to the xy, e to the I xy dy is a delta function, so the integrate of this dy is a delta function at x. So sometimes you get Gaussians defined on a subspace. Delta function means that you're looking at just a subspace. But to the best of my knowledge, there isn't a complete theory of Gaussian integration. This is kind of bizarre, but to the best of my knowledge, there isn't a kind of completely functorial theory of Gaussian integration. And I think I have one, but it doesn't yet match with Tangles fully, so that's why it's not done. Yeah, that's all I have to say.
Thank you. Any questions?
I remember in the original paper of this Kashayev invariant, he actually used some like orthogonal polynomial, this Hermite polynomials.
Yeah, but only first 3.
Yeah, only first, but do you have something here? Or some kind of Fourier transform in this over here?
No.
Okay. So it has nothing to do with this orthogonal polynomials.
Not that I know.
Leading trees from matrix, this I didn't see before.
Sorry?
Usually signature is calculated from Seifert matrix, calculated on the basis of homology
Oh,
intersection.
so you're asking...
Yeah, where it comes from, this matrix.
This matrix.
Yes.
Sorry, this matrix you presumably know where
this
they
I know.
come from.
Left.
These
yes.
ones. So these one actually have a story. So when I first, at some point in early 2000s, I started working on the knot atlas, and I kind of wanted to compute all the invariants. And the real reason I wanted to do it was because I like to program more than I like to program nice mathematical things. So I wanted to compute the invariant of the signature. So sorry, I wanted to compute the signatures of knots, and I barely knew what the signature is, but somebody told me the definition, and I came up with these formulas. But I'm pretty sure that someone was still in the room, so the credit should go to two people, but I don't remember who the other one is. But basically, it's half mine, and I don't know who the other half is. But if you want to know where these matrices are coming from, and then 20 years later, I discovered that these matrices were not known, that this was not known. So I don't know.
But you extract them from cipher intersection form.
I can tell you where. I can tell you how. So suppose you have a knot. There is this usual ciphered and the term and intersection forms, etc. But for that, you need to construct a ciphered surface, and to construct a ciphered surface, you have to be smart, and I'm not smart. So what do? So you do the first part of the construction of the ciphered surface. The first part of the construction of the ciphered surface is to turn these into is to smooth at the, God, did I do the right smoothing? I didn't do the right smoothing. To smooth in the crossings. Then you multiply by the interval, so you get curtains here. Basically, each of these lines become kind of a standing curtain because you multiply by an interval. And then you add twisted bands where the crossings used to be. And then the last step of the construction of the ciphered surface is to glue disks on the bottom. So I add the twisted bands at the top, so I glue disks at the bottom. If I don't glue the disks, I don't get the ciphered surface, but I get a surface on which the ciphered form can equally well be defined, and it has the same signature because the homology is bigger, and so basically by gluing these disks, the only thing you do is you demonstrate, you restrict to a basis. So like if you compute the ciphered pairing for the thing before gluing the disks, you get a degenerate matrix whose signature is the same. So you just compute this. But this is completely local, so the basis of H1 of the surface I got by doing the curtains and the bands is you basically go around each of the faces. So the H1 is just one generator for each face, and the cipher pairing is just coming from how the twisted bands are connecting the nearby faces, and that's what you get here. That's what you end up getting. So it's, I'm kind of amazed that people tell me it was not known. Anyway, that answers your question, I hope. Yes?
So you were speaking about signatures, and then you mentioned Alexander polynomial, but the whole construction can give more stuff, or well, because right, it sounds like a rather general story of those plane algebras. What kind of what can give
So
more depth?
that story in itself, you know, there is an extremely unlikely but theoretically possible, you know, there are, so I think this is the question, it's one of the questions here, but you know, so there are the Tristram-Levin matrices, there are the Kashayev matrices, maybe there are more matrices, the Alexeyev matrices, so maybe there is another pair of matrices such that if you feed them into my machinery, they will tell you that Reidemeister 1, 2, and 3 are satisfied. In principle, you can solve for it by undetermined coefficients, you know, you just need 32 coefficients, you feed them into the machine, you see if there are outputs. In principle. I haven't done it. There might be more, they may give you something new, I don't know. I'm not having high hopes, to be honest. Okay? So that's one answer. The second answer is that a year and a half ago, I gave a talk in Geneva, in the Jones conference, on a subject which I think is much more exciting. But since I gave it a year and a half ago, I couldn't repeat it today. And this is this higher loop invariant. So row 1, I talked about this invariant, or these formulas for an invariant that Roland van der Veen and I found. And those formulas, roughly speaking, were constructed by taking that same matrix which constructs the Alexander polynomial, and that same matrix whose determinant is the Alexander polynomial. Sorry, there are 50 such matrices. So taking one of those matrices whose determinant is the Alexander polynomial, and instead of computing the determinant, you compute the inverse, and then you do something quadratic with the entries of the inverse. And then you can ask yourself, maybe other matrices that compute the Alexander polynomial will also have a corresponding row 1 invariant. So in particular, those Kashayev matrices, and also the Tristram-Levin matrices, so these matrices that I've shown, also compute the Alexander polynomial. So with a little bit of more effort. But I mean, so you can ask yourself, is there something else you can do with them? So that will give you formulas for row 1. And the real reason I'm doing this is because I convinced myself at some point that I don't understand the Alexander polynomial and I don't understand signatures, and it's a bit ambitious to try to do row 1 when you don't yet understand row 0. So I don't know if it answers your question. One day I will want to do similar things to get higher invariance, but it will be similar to what I talked about a year and a half ago, not quite to that. And that is really just the background.
Yeah, maybe I can comment on that by saying that besides of Alexander and signature, the quadratic form certainly contains more information, right? The invariant information. And what I can say, you can make a Gaussian sums of those quadratic forms over finite fields.
I know you, and I forgot where I know you from.
Christina.
Christina,
Yeah.
good. So yes.
Yeah, so the question was related to number 4, the braids and broad representation. So can you, in the Alexander story,
Yeah.
can you see the broad representation showing up?
No.
What do you expect?
Yes. That's why it's a question. So the Burat representation should be somehow hidden in these 4x4 matrices. I don't know much.
No further questions? Thank you again.